we're talking more about the regression line that goes on the scatter plot, and we kind of found that yesterday on the calculator, because the screen we had to go through to get the R value, the correlation coefficient, also did the linear regression for us and gives the equation for that line. But I want to talk a little bit about how that's found. You know, when you first learned about lines best fit, you probably just took a scatter plot and took a ruler and tried to draw a line that went kind of through the middle of it and hoped for the best. And close enough was, we just said close was good enough in that case. And then you kind of got to the point where you could use your calculator to find it. But there is an actual method that's used to calculate that unique line. So let's look at this one. We're going to make a scatter diagram here. We'll do this one by hand. It's not too hard to do. So scatter plots we talked about yesterday, you can do on your calculator very easily, just by entering the data into L1 and L2. And we can do it by hand. You're just plotting the x's and the y's. So at x, I need 0 through 6. And let's see, my y's, I'm going to go up to 6 as well. And then we're just plotting these. So 0, 5.8, 2, 5.7, 3, 5.2, 5, 2.8, 6, 9, and 6, 2.2. So if I haven't taught you the process and I told you to find the line of best fit, you would probably try to find an equation that goes through this and uses a couple of these points, right? Now you want it to follow the general pattern. So we have to think, you know, if I were to draw a line, what might be on here? So this point seems a little away from everything, so I probably wouldn't use it. Maybe I'm going to use the 2, 5.7. And I need another one, maybe like the 6, 1.9. Are those the best 2 points to use? Not necessarily, I just said to pick 2. So if I wanted the equation, how do you write the equation of our line? Yeah. Go find the slope. So we have our equation, and then we could graph that, right, easily enough. I'm just going to kind of use the 2 points to draw my line so we know it goes through both of those points. So it's something like this. Is that a perfect line? Probably not. kind of the best thing I can do without any kind of formal calculation. And once you have a line, you can make predictions. If I want to predict y if x equals 3, so we plug that 3 in. And so we get 4.75. So that's kind of how a line of best fit works. Follows the general trend of the data. It's an equation that we could use to make predictions about points that aren't on there. But we know that line isn't perfect. And so there's always a difference between the value that our line is going to give us and the value we might actually see. If we look at this, did we have a point when x was 3? Yeah, and that one was 5.2, but we got 4.75. So there's a difference between those. That difference is what's called the residual. So residual is the difference between the observed and the predicted value. This is on your formula sheet, chapter 4, first bullet in the second column. Residual is observed y minus predicted y. Observed was what actually happened. So if we look, when x was 3, the actual value from the table was 5.2. Minus the predicted is what we would think when we plugged in the calculator. So 5.2 minus 4.75 gives us a residual of 0.45. That's also called the error. So that's how far off we were from our approximation. So the best line would be the line that makes these errors as small as possible, right? We want it as close to the real data as we can get. So we need our errors to be as small as possible, or these residuals to be as small as possible. That is the least squares regression line. Notation for this, it's a y hat is our predicted y, so you'll see that in your formula. And this is just the line that minimizes. I could write and so there is a formula for this. A lot of times we're just going to do the calculator, but kind of like the other things, I want you to know where it comes from, that it's not just something made up. And so if you look on your formula sheet, so the next slide, you don't necessarily have to write this big massive thing down. It's on your formula sheet. Under chapter 4, it's the second bullet. The equation of the least squares regression line is y hat, so that's our predicted value, equals b sub 1x plus b sub 2. Okay, that's just mx plus b, front page. Does everybody see it on there? B sub 1 is just representing our slope, and that's found by doing R, which we saw R yesterday. What is that? Correlation coefficient, times standard deviation in y divided by standard deviation in x. The y-intercept is found by doing y hat minus b sub 1 times x hat. Or sorry, y bar minus b sub 1 times x bar. So this requires a lot of different information. We're not going to have to do all the calculations by hand at once on this, but let's take a look at an example and kind of walk through this. So I want to use this data to find the least squares regression line. I want you to go ahead and enter this into the calculator so we can get some information from it. So let's go to stat, calculate one variable statistics for a minute. Or sorry, not one variable, two variable. Stat, calculate two variable statistics. So x is L1, y is L2. All right. So here's all of our information. So if I want the least squares regression line, looking at our formula sheet, let's practice using this. We know we're looking for y equals mx plus b. Okay, the slope, it says b sub 1, that's your slope, equals r times standard deviation in y divided by the standard deviation in x, right? Do I have my r here? No. Let's go ahead and calculate the r. Now, in doing this, it's also going to give us the equation, but I'm going to show you how the equation came about. So if we go to stat, calculate a linear regression number 4, enter through all of this. If yours doesn't have an R, that means you grab the calculator where the diagnostics are not turned on. Does anyone have that problem? So go to catalog. So really, we now have the regression line, but I want to show you where it came from. So the R is negative 0.9456 times standard deviation in y. So if I look at my calculator, standard deviation in y is 5.6125 divided by standard deviation in x, 2.4495. So if we do that calculation, we get negative 2.1666. Isn't that very close to this day? Why is it not exactly the same? Rounding. I rounded all those numbers to 4 decimal places. The y-intercept, go back to your formula sheet. That b sub 0 is your y-intercept, and it's found by doing y(r), so that's the mean of y, minus what we get for b sub 1 times x bar, so the mean of x, which is 4. And the 18.6664. Again, only slightly off due to rounding error. So, our line of best fit, we call it y hat just because it's the predicted value. 2.1666x plus 18.6664.
Where do we get the 4?
X bar, the mean of x. So again, most of the time we're just going to rely on our calculator to get that, but I wanted to kind of show you where the calculation came from and help you understand the formula on your formula sheet. What's wrong? Really? I don't know that I believe that. Have a question you want to ask me? Alright. Other questions? Yes. The y-intercept. So if you look at this,
It's y equals ax plus b. So you're saying that there's a third x plus.
you have to be a little bit careful when you use these lines. You know, this value, or this line, look at all my points. We have points 1, 3, 6, 7. So would this be probably a good line if x were 20? Not really. It's probably a good line for values close to those, but if you have a value that's really far away from everything we use to write the equation of the line, it may not work as well. We call that outside of the scope of the model. If you ever hear that, it just means we have an equation, but it may not still work because this point is so far away from all the other points we use. We can't expect the same patterns to continue. All right, so one last problem. We're going to use our calculator to try to solve this. So here is a table with some golf data. I want the least squares regression line. So I want you to do it on your calculator. So first you have to enter your data into L1 and L2. And then where are you going to go to get your line? Stat, calculate, number 4. Okay, so it says y equals ax plus b. So a is your slope. B is your y-intercept. And since this is our prediction line, we usually put a hat on it, y hat. Did everybody get that line? Okay, let's talk about drawing it. So if I wanted to view the scatter plot right now, what would we do? You go into your stat plot, make sure plot number 1 is turned on to a scatter plot, and if you zoom 9, you should be looking at a scatter plot. Everybody practice turning that on, and if you don't get scatter plot, let me know. If you go to zoom number 9, it will zoom to where your data is at. Yep, so that's a scatter plot. And then go zoom number 9. So zoom stat. Okay. So now if I wanted to see my line of this best fit, you can go back to your y equals. And in my y equals, I want to type in this equation, 3.1661x minus 55.7966. Look at my graph, I have a scatter plot with a beautiful line of best fit drawn. We can see it's a pretty good line for our data. Okay. if I wanted to predict the distance at 103 miles per hour, what would I do? Plug it in for x. And we get 270.3 approximately. Distance was measured in yards. Okay, so now if I want the residual, anytime you forget what something is, look at your formula sheet. It says residual equals the observed y minus the predicted y. Okay, observed is what we saw in our table. So that was 274. Predicted is what we based our equation, or what we got from the equation. So 274 minus 270.3 gives me a residual of 3.7 yards. So my prediction was 3.7 yards higher than the actual value.
Why would you give that specific one?
Because we're finding the residual for part C, and in part C it told us the x was 103.
Okay.
So we could technically, every single point on the table, we could calculate the residual for every one of those. Alright, last question. Slope and y-intercept. What do those things mean? So we know slope is like y over x, right? My slope is a positive. Y is in yards. X was miles per hour. So that tells me the ball will travel 3.1661 yards per mile per hour. Or for every 1 mile per hour harder you hit the ball, it will travel an additional 3.1661 yards. Y-intercept, that's like when x is 0, so it's like saying the starting position. Is negative 55.7966 yards. Or if x is 0, then your y value is this. Alright. Questions? Can you guys believe Grant couldn't hear me talking on the video yesterday? I don't understand why that might have been a
Actually,
problem.
you can't hear it all. Period. Like about
He's
his
lying.